guest today is Rocky Duan. Rocky did his undergrad and PhD at Berkeley, where he pioneered some of the earliest deep reinforcement learning work, including building what became the origins of the OpenAI gym. Next, Rocky, by then still only 21 years old, was one of the very first hires at OpenAI, where he pioneered some of the earliest meta-learning work, including first modern era papers on learning to reinforcement learn and learning to imitate. For the learning to imitate work, Rocky invented an architecture actually quite similar to today's attention mechanisms that became popularized through the transformer. In 2017, at age 23, Rocky left OpenAI and co-founded Covariant, where he still today is the CTO and develops artificial intelligence for the next generation of robotic automation. Aside from being well known to be incredibly productive, most often quoted as at least 10 times more productive than any of the other exceptionally productive people you might know, Rocky is also widely known as one of the nicest people ever. Rocky, so great to have you here with us. Welcome to the show.
Thanks, Peter. It's my great pleasure to be on this podcast.
So good to have you, Rocky. But before diving into today's conversation, I'd like to thank our podcast sponsors, Index Ventures and Weights and Biases. Index Ventures is a venture capital firm that invests in exceptional entrepreneurs across all stages from seed to IPO. With offices in San Francisco, New York, and London, the firm backs founders across a variety of verticals, including artificial intelligence, SaaS, fintech, security, gaming, and consumer. On a personal note, Index is an investor in Covariant, and I couldn't recommend them any higher. Weights and Biases is an ML ops platform that helps you train better models faster with experiment tracking, model and dataset versioning, and model management. They're used by OpenAI, NVIDIA, and almost every lab releasing a large model. In fact, many, if not all of my students at Berkeley and colleagues at Covariant are big users of Weights and Biases. Rocky, let's start with what you're doing today. You are co-founder and CTO of Covariant, which of course we founded together. What does Covariant do?
At Covariant, our mission is to build universal AI that enable robots to learn and operate in the real world, to assist humans with repetitive and laborious tasks. And today we are starting with the warehousing and logistics industry. And this is an industry where labor shortage and high turnover rate is a very real and growing problem. And if we look at what the human operators are doing today, they need to perform highly repetitive tasks that involve transporting goods from one place to another. And this sounds simple, but turns out to be very challenging for traditional automation to tackle entirely. And at Covariant, we are building AI-powered robotic systems that automate various processes involving currently humans using their hands to manipulate objects, like picking things up, scanning them, and placing them to various destinations.
Interesting what you said there, Rocky. It seems simple to do pick and place. In fact, I think most people listening to the podcast will probably be like, okay, I can definitely pick and place some objects in a warehouse. That seems very feasible. And it doesn't require extensive training like becoming a medical doctor or something like that. But it's hard for robots, as you said. And in fact, some people have called it the holy grail of robotics if you can solve warehouse pick and place. Can you dive a bit deeper? Why is it so hard to make a robot do that?
Yeah, it's a really good question. And just want to echo that it's something that us humans can do so easily without thinking about it. And in fact, we can even do it blindfolded. And on the other hand, it is indeed really challenging for robotics, and it's not solvable by just programming robots to follow instructions, which is why it's been challenging for traditional automation. And if you think about it more carefully, it's actually pretty non-trivial. First of all, the incoming objects that you expect the robots to handle are typically presented in a very unstructured layout. Every action that is to be done by the robot is different, and you can't just program the robot to repeat the same instructions again and again. And second, there's a wide variety of different objects that the robot will need to be able to take. And it's impossible to pre-configure the system to memorize this large number of different objects. What this means is that the AI system needs to surely generalize its behavior and its understanding to new situations. And this further distinguishes this task from more traditional robotics.
It's hard because of all the variations you described and all this challenge involved. You can't directly program. So what's the alternative? How to actually solve it? Have you solved it?
So what distinguishes covariance AI and traditional techniques is that we use machine learning and more particular deep learning, which has been a very promising technique being popularized in recent years thanks to the advances in big data and more powerful computing. And what's different about this approach is that rather than directly programming the robots in terms of code, we actually program the robots in terms of data. And we use those machine learning and deep learning algorithms to distill knowledge out of those data. And so those data can be in various forms. They can be in terms of human provided annotations, or it can be in terms of robot's own experience interacting with the world. And through those data, the robot learns what behavior leads to actual productive outcomes, and which behaviors lead to not productive outcomes or even errors that we want to avoid. And through this learning process, the AI system generalizes to new situations and learn from its own mistakes. And I will actually say that very confidently that with those techniques, pick and place is no longer something that's kind of scary for automation. And we are seeing very promising results with the systems that we are actively deploying to our customers.
You talk about systems that are being deployed to customers. What should I envision there? What is an example of what this could look like in a warehouse?
There's actually many different forms. And so in some cases, we are actually just providing the brain to an overall automation system, where basically we provide our own camera system and our own software that understands the environment and thinks about what action then to be taken. And then we work with other partners to provide the entire automation system. So those partners might be very well established warehouse automation providers. So in those warehouses, if you go there, you might see a lot of like shuttles, automated vehicles moving around. But before Covariant, you will see human workers still stationed next to those automation systems, where they need to still manually picking and placing things. And with Covariant, you'll see our camera systems intelligently reasoning about the environment, instructing robotic arms. In this case, it'll be provided by our partners, which then perform the task of picking and placing objects automatically. And in parallel, we also are deploying whole systems ourselves. And we have various products which I'm happy to dive into more detail. And in those warehouses, you actually see Covariant design entire systems operating in various segments in warehouses.
Got it. So I am curious, what are some examples of these full solutions that are being delivered
Yeah. So basically, our systems are automating various steps in the order fulfillment process, typically in the e-commerce, logistics, and some rising new industries. And there's different products because each warehouse is kind of built differently, although there are a few categories depending on how automated they are already. One example is what we call a robotic footwall system. So this is a system that can be deployed to warehouses with a relatively low degree of automation. So this system will process an incoming batch of mixed product objects, which have been picked up by human pickers in upstream. They come to the system, and the task of the station is to sort those objects into different orders, typically in the range of between 20 to 80 orders. And it's called put wall because there's typically a few walls around the robot or human operators before Covariant, where the robot will need to pick objects one by one, scan them, and according to the order information, put them onto the right slot onto the wall. So this is one example. And as I mentioned, there's also cases where if the warehouse is more automated, if they're employed with shuttle systems, in those warehouses, human workers no longer need to move around in the warehouse, which can be quite exhausting. So in those cases, the codes where they need to pick objects from will be presented to humans via some shuttle system. And those stations where the human workers are standing still become a potential integration point for automation. And previously we would call those goes to person picking, and now I think the new popular term is goes to robot picking, where we basically will have a robot arm waiting for toads to arrive one by one, and according to a system instruction, picking either one or several objects from each toad. And those toads will typically only contain, say, one type of product or a few type of products, placed into different compartments inside the toads, and then placing them either to another toad or some downstream destination.
Going back to the technical side of things, when you said now with deep learning methods, we are able to teach the robots pick and place, right? So we can go beyond traditional programming of robots. That's a pretty big umbrella term. Deep learning, data. Can you say a bit more? What is under the hood? What are the key ideas that allow the covariant system to actually understand how to do pick and place one level deeper or two levels deeper than lots of data and deep learning?
One of the key ideas is deep reinforcement learning, which I've personally had the fortune to work on during my PhD study and during my time at Covariant. My time at OpenAI. And of course now at Covariant. So there's actually, I guess, two key ideas that when combined becomes the term deep reinforcement learning. So I guess one is deep learning and the other is reinforcement learning. And the idea of deep learning is that basically we have all those data, and we want a learning system to be able to first of all be able to interpret or understand all those data or explain the correspondence between certain inputs and outputs. So we need the system to be very expressive. And for more traditional machine learning approaches, we typically do this by hand engineering certain features, extracting them out of the data we have, and then use simple models to try to fit those data. And the performance of such systems highly depend on the quality of features that we can come up, and require specialized knowledge, all the domains that we're trying to tackle. For example, for images, you need to have domain understanding of image processing, computer vision, in order to come up with like high quality features. And what sets differently apart is that rather than hand engineering those features, we try to come up with those architectures of neural networks, which are very expressive parameterized models. And they can have vast capacity and wouldn't suffer from the problem of underfitting, which is a common problem that we will encounter if we try to use more simplified models. And on the other hand, not only does it not underfit, we can impose certain prior knowledge into how we design those architectures, so that you can achieve good generalization performance. Some of those prior knowledge involve using a convolution architecture, which basically leverages the translational invariance when we think about the computational process that should be involved with, for example, images, text, or other data with those kind of locality structure. And attention will be another recently popularized building block in those architectures, where we want to allow the architecture to focus on one portion of data at a time, and also querying other maybe not very localized feature information by a kind of a lookup operation and aggregate operation. So it's very powerful because we don't really need to prescribe how exactly the computation happens in terms of code. We just need to have some intuition about the kind of computation that we want the algorithm to perform. Design the architecture that enables those priors, and then with those we can build powerful systems that actually turns out to work quite well across very different disciplines. Another key idea that is reinforcement learning. So I guess to explain reinforcement learning, we need to look at maybe other paradigms that are popular in machine learning. I think the most popular paradigm used in the industry is supervised learning, where we will provide label examples where say the input can be some images, and the labels on them could be different classes of objects that we want the system to detect. For example, this is a bottle, and that is plastic bag, and we need to collect all those data using prior knowledge of human. So this can work well in some domains where collecting those supervision is cheap. But there's in some cases, collecting those can be very expensive. For example, if you want to acquire like a 3D understanding of the world, it's actually kind of non-trivial to collect supervision about how distant everything is away from you. And sometimes it's just that we are actually not very good teachers to the robots. For example, if we want the robotic systems to reason about different strategies to grasp objects and moving them, those are actually pretty challenging physics problem that we'll need to solve. Of course, we can say that we can do that easily with our hands. But if we look at today's hardware, actually, we can't just use a human hands equivalent. We need to actually design some different hardwares to serve the needs of different products that we need to tackle. And even with human equivalent hands, the control of them is actually highly non-trivial and not something that we can can just kind of easily provide labels to the robots. So in those situations, it's actually more important for the learning system to learn from its own trial and error. What this means is that we want the system to kind of explore the environment using different strategies that it can come up. And it'll get some feedback from the environment, like if it successfully picked up something, it will know that it's a good thing, and it should reinforce such behavior more often. And if it did a bad thing, like it missed the pick, or it picked something up but dropped it, or even worse, like it picked up something and maybe squeezed too hard and damaged something. So those will be negative signals to the system that we want to avoid in the future. So I think the idea of reinforcement learning is that we want to design algorithms so that those learning systems can improve itself from just those signals. We're really not prescribing, the robot, you should first detect objects in the scene, do some calculation of the physics properties, and then based on that, do some maybe lookup from your database of pre-configured strategies of how to look them up. We're really just saying, this is the space, this is the range of actions you can explore. This is good, this is bad, go figure out the rest. It sounds almost too good to be true, but it actually turns out to work really magically well sometimes. If we design good algorithms, have good setup, and have enough data to feed to this system and the learning process.
Now, the general trend in artificial intelligence right now is a trend towards foundation models. What role do you expect them to play, or are they already playing maybe at Covariant?
The rise of foundation models is a really exciting development in recent years. Maybe I can first explain a little bit what foundation models are. So those are models that are trained on a vast amount of diverse data. And as a result, they are so powerful and they can be adapted to many different downstream applications. And I guess the most notable example in recent years is probably GPT. So this is a family of large language models developed by OpenAI. So these models are trained on a tremendous amount of natural language data from the internet. And they have been used to power many exciting applications. Like one example is GitHub Copilot. So this is a service that provides intelligent code completion suggestions. Actually, I use it on a daily basis and find it to be really amazing and a very good productivity boost. And another example is, of course, ChatGPT. It has just been released last November, but it has been absolutely mind-blowing. It's the most powerful AI chatbot that I've ever seen and played with. So the connection between foundation models and covariant, so it's actually quite connected. If we think about covariance definition of building universal AI, and I think this idea basically contrasts the kind of still the mainstream approach right now of applying machine learning industry, where we kind of train different models to solve relatively narrowly defined tasks, given some data sets that we collect in some specific domain. And instead, our philosophy at Covariant has been to try to develop a common AI system. So we actually call this Covariant Brain. It's kind of our brand name for our AI system. And we hope that this single brain can power all of our use cases. And the rise of foundation models, very similar in philosophy, they kind of give us some very exciting future directions where where I think we can take our technology to the next level. So one example is that we can leverage internet scale data of like images, videos, and text that are being used to train those foundation models, and we can use them to improve the generalization of covariant brain. So maybe one example I can give here is that there's one further challenge of like say templates is that there's a lot of long tail scenarios that we need the system to understand and react to. One such example is that let's think about the robot picking up copper boxes. These are probably the simplest possible objects that you can expect a robotic system to pick. But it's actually not that easy sometimes. For example, if the box is not sealed tight, and when you pick it up, the lid can actually open. Then what can you do in that case? So I guess this will be kind of an exception scenario. And you might need to do different things depending on which direction is the lid open. If you are picking up the lid, and it's just open slightly, maybe you can still safely place it to the destination, but you will need to move very slowly or only in certain motions. If it's open on the bottom, maybe you actually will need to more targetedly do different actions, or you might even need humans' help in that case. And it's very important in those for the system to be able to understand those different situations. And if we think about traditional machine learning approaches, or even if we say, well, let's use deep reinforcement learning. If we want to use, say, supervised learning, what we'll need to do is collect enough data where there's some diversity of different objects with the lid open, and then provide human annotations. Like this, in this example, the lid is open on the top. In another example, the lid is open on the bottom, and so forth. And it can be actually quite costly and will take a lot of time to collect those examples, given that it's kind of a rare event. And even with reinforcement learning, there's actually some challenges here because how would you give the supervision to the robot in this case of what it should do? You will need to come up with some reward signal to the robot. And in contrast, I think what the internet scale data and what the foundation models inspires us with is that we can actually leverage all those kind of free label data out there to give our system some common sense understanding. Like for us humans, we probably don't need to see like 100 or 1,000 examples of lid open to know this concept. And we probably can't even recall what was the first open lid that we've seen before that taught us this understanding. It's kind of just intuitive common sense knowledge that we acquired. And from our analysis of the foundation models is also something that these models seem to start to possess, basically acquiring a common sense understanding from those internet scale data. I think it's very promising that we can try to leverage either those models, the data, or the training techniques to equip our covariant brain system with such common sense understanding, so that for those long tail scenarios, we can program or have the systems understand and adapt quickly in those situations.
That's really exciting, of course, because ultimately the long tail, if you don't address it correctly, you're just not producing any value because there's too many exceptions called. And this idea that foundation models trained on internet data can bring in common sense to help understand robotic picking. I'm super excited about this because it's in some sense a very interesting form of generalization, because not much internet data involves bin picking scenarios. Usually internet data is, most people would say it looks more interesting than bin picking scenarios, but somehow there can be a transfer of concepts like a lid that's slightly open, that's fully open, a box that's damaged, something packaging that has come loose, all those things can somehow transfer over, which is really exciting that those things are becoming possible. When you think more widely about the AI robotics frontier, Rocky, let's say, not specifically to Covariant, of course, Covariant is at the frontier, but if you think more broadly, what are some other things that you see at the frontier that get you very excited?
Of course, I guess I'll wear a bias lens due to my experience at Covariant. But I think some of the frontiers, they're definitely what we have an eye on, but are definitely not specific to the kind of applications that Covariant's working on. And I guess I will mention two things. One thing is how we think about having extremely reliable systems, and how AI can enable that. I think so. This maybe one example other than Covariant I'll give is autonomous driving. It's a hugely challenging problem. Has huge market size. The challenge, one of the challenges is that you really need those systems to be highly reliable because the cost of error is so high. And in some sense, if we think about the technology stack needed to power autonomous driving, there's actually many common components to what we need to build here at Covariant, like perception, understanding of the world, and planning or control to try to figure out what the robot, like either arms or autonomous vehicles, need to do in the world. And why is getting high reliability so challenging? One of the reasons is that those building blocks of the systems. So we are in both cases we need to employ a lot of AI powered systems, and they're seldomly by themselves 100% correct. And each component can make their own mistakes. So in those cases, I guess like how would you then build an overall very robust systems? And of course, one direction will be to try to push individual components to higher and higher accuracy, like inventing new ways to leverage broader amount of data, try to do unsupervised learning, try to invent new architectures and so forth. But a different angle is how can we kind of compose those components so that maybe some components can help correct other components' errors, or can you have each component like a image detection module, some visual semantic prediction module? Can they better understand when they are uncertain about the situation, when it is more likely to make an error, so that we can, so that the system overall should be in a more alerted state if it's actually in a new situation. And maybe we can fall back control to humans, or spend more compute, maybe at the expense of reaction time, or depending on what trade-off is reasonable for it to make. I think those kind of like system level questions are actually quite important and not very well studied yet. So that's something very interesting to me. Another theme related to reliability is like how fast we can improve a system's performance. And there's several axes to measure this. One is like how much data is needed, and another, I guess, is like how much time is needed to, for example, collect those data or retrain the model. And so the experience at Covariant, I will say that if we have a well-defined problem that we want to solve, with enough data and enough time to train the model, we can usually get to very good performance. But time is money, and it's also not enough to say, let's just collect data and wait for a while to get a good performance. And there are cases where we actually need the system to be able to very rapidly react to changes to the environment. A very, very real example to us is that, let's say if a product goes on sale. And this might only last for a few days or even a few hours. And maybe suddenly, your system, cannot handle the situation anymore. Maybe to give a more concrete example, let's say you're picking up like, bottles, that are like smooth, on the surface. So every place on it, is, pickable. So the robot is, very high performing. But suddenly, maybe a new product, comes out where, half of the product surface actually is, bumpy, and cannot be handled by, the same, gripper, that we use. So if your system can't adapt to such change quickly enough, then you'll suffer from, loss of productivity, for the period where you are still improving your performance. So I think there are different techniques that are being explored, for example, in academia, or at Covariant, about like how to make the system, be able to improve more quickly, using different approaches. And of course you can, characterize it with some, common knowledge, common sense. But there are other, exciting possibilities which I'm happy to dive more. But overall, like, I think those two, like getting highly reliable systems and fast improvability, will be, in my mind, the AI frontier for robotics.
Yeah, very interesting, Rocky. And I really like one of the things you mentioned in the first part, which is the notion of a system that can take a step back, understand when there is uncertainty, maybe use more compute cycles to make a decision as needed, rather than always going through the same amount of compute, even though sometimes things are easy, sometimes things are hard. I think that kind of innovation, it's very different from pretty much anything out there today in practice or in research. It seems the default is a neural net with a fixed depth. Things get processed by that neural net and something comes out and that's it. There's no room for deciding to spend more time. It's just everything's gone to the neural net and done. And so that option, even though clearly for humans it exists, right? This notion of taking a step back, the current standard paradigm doesn't have it inside of it. You need to step out of it, invent something different. And I really like the second example you gave, because I mean, by default, even for myself, when I think of the long tail of things our robots run into, I think of, long tail, a lot of things, but it's in the tail. It doesn't happen too often, and maybe it happens once now, and then maybe an hour later something happens. But I love your example because you're essentially highlighting that you could have a window of several hours within which the only thing you get to see is the long tail over and over and over, and you need to learn on the spot or it's too late. And it's very interesting because that's not how I think about it by default, and I think most people, but the reality is that it happens a lot. With these sales, that all of a sudden something completely new, packaged in a completely new way, complicated packaging, fancy packaging, and so forth, to help them with the sale. And all of a sudden, much harder to pick. You need instant adaptation, or it's too late. Now that's on the technical side. How about on the commercial, the application side? You've talked about warehouse picking. Obviously, you've mentioned self-driving cars. Are there any other AI robotics applications that you see on the horizon and that are exciting to you?
I can probably answer this in kind of like the two perspectives. One is like things that I think Covariant can potentially expand to in the future, and also more widely, like maybe it's not within Covariant reach anytime soon, but I'm personally very excited about. So in the first category, there's of course a wide range of different use cases that we get exposure to from talking to our customers. And one angle is that if we start from the current systems that we are selling, if we look at the upstream and downstream processes, some of those are automated, but some are still manually done by human workers. And those are potential future directions for us to automate so that we have a more integrated automation system. And one such more concrete example is that going back to the earlier robotic footfall, where the robot is sorting items in different orders. So currently after this is done, let's say all the items of a given order have arrived in one slot on the wall. To the other side of the robot, currently we actually still need human workers take all those items and then put them in a shipping box to be shipped out. And this can sometimes actually become a point of bottleneck to the overall system's throughput if the human hacker in this case cannot keep up with how fast the robot is performing. And we've actually seen this happen. And if we can further automate the packing process, this can, on one hand, potentially improve the throughput of the overall system. And another benefit is that we can potentially further improve robustness, since that we basically introduce more AI touch points in this overall system. And when the system downstream is, for example, like rearranging those objects in the shipping box, it can more intelligently check for any errors that may have been made by the earlier steps in the process. So this can potentially further reduce the error rate of the system, or as we've observed, actually our system is already performing pretty well. It can potentially offer some trade-off. Maybe like the upstream process can be slightly less careful, maybe to trade with higher efficiency, and rely on the downstream system to provide this check, so that as a whole we obtain a system that is both sufficiently reliable and much more productive than the system state. So these are so outside of Covariant, I guess I'm also quite excited about some opportunities that I already see, like maybe other startups are tackling, or maybe could be tackling in the future. And maybe one thing that's relevant to, not relevant, but like just interesting to me and may not have like huge direct commercial value, but I think it could be very impactful, is the potential application in basic science, where we can use robots to basically automate scientific experiments. And it's relevant to me, I guess, because so my wife, Zhao Yu, so she has a PhD in organic chemistry. She did her PhD in Hong Kong. So through that, I kind of got a glimpse of like basically some quite laborious tasks that those scientific researchers need to perform in their labs on a daily basis. And I guess for chemistry, it's maybe an analogy is like cooking a meal that's maybe not very tasty, and it's like actually can take a very long time with many different steps that you need to perform with great precision. And sometimes it can even involve potentially like hazardous materials. And so you need to be very, very careful with those. And same for a lot of like biology experiments, that require a lot of manual labor. And I'm really excited about the potential of robotic automation. I think the direct value that it provides is that those researchers can then focus more of their time on designing experiments, thinking about future research directions, and analyzing the results of those experiments. But also, I think there's value in more standardized procedure of performing all those experiments, making the results more reproducible. We can collect more data, have the process being more observable with all the sensors we have deployed. And also there's chance for greater economy of scale. So I guess analogy for computer science would be the kind of cloud computing platforms that are being provided by say Amazon, Google, Microsoft. And I can imagine similar like cloud labs that can provides the experiment needs of many different researchers in those basic science domains. So I think all of those are, I've seen a few startups in those domains, and there's also academic papers about like using robots to speed up experiments. So very promising development. I guess it's a bit further away from covariance, but there's actually some shared challenges and overall quite exciting to me.
I think it's a really exciting thing to be thinking about, Rocky, how AI robotics could actually power a scientific revolution in any kind of sciences where physical experimentation, largely manual experimentation right now, is the bottleneck. And it's something that I don't think too many people are thinking about yet. Of course, you're not going to be the first one to mention it here ever in the world, but I think the opportunity is ahead of us. And yeah, it'd be very exciting to see something play out there that really revolutionizes potentially medicine, at least invention of new medications, invention of new supplements, invention of all kinds of new compounds, materials, and so forth that are currently bottlenecked by experimental cycles, sometimes hazardous, as you mentioned. Now, when I think about when we started Covariant, at the time, we, including you, of course, we left OpenAI, which was a pretty great place to be. I'm kind of curious, what made you at the time so convinced that, despite the fact you're at such a great place already, that founding Covariant was the right thing to pursue for you?
Yeah. So let's first of all, OpenAI has been a great place for me to be. There's so many talented people working towards a very ambitious goal, and I really learned a lot during my time there. So at the time, I was closer to the robotics team at OpenAI. I think back then the focus has been more on kind of pushing the frontier of basic learning algorithms and demonstrating them on very, very challenging tasks, like what we later learned about, like say using robotic hands to solve Rubik's cubes. So these tasks were a little bit further away from things that potentially can be actually viable in the near term, generate like near term commercial value. So how all of this connected to me is that, so first of all, I guess like, actually there was an earlier podcast, where Peter Chen, our CEO of Covariant and also a long-term friend of mine, explained his side of the story. I remember him mentioning there's like a sketchy but delicious Chinese restaurant where we were like discussing how we can push our research to the next level. So I guess this is my version. Actually, honestly, I didn't remember which restaurant we were in, or whether it was at a restaurant, but also my memory was vague. What I do remember is that, I kind of had this realization that to solve robotics, it's not enough to just develop and improve algorithms. But it might be more important to get access to the right data. And I kind of have a more general notion of data here, where it doesn't just include like, say, images, text, videos, human annotations, or whatnot, but it actually also includes the range of different tasks that we want the robot to learn to perform. And this is important also in terms of how we evaluate our advances in algorithms. Like ideally evaluate on the things that that's actually relevant to what we want them to solve. And it also maybe matters to like what kind of algorithms you can come up with, or can be made powerful depending on the scale of data you have. And on the other hand, it's kind of limited in terms of what tasks you can have access to in academic setting. And my belief was that to really make AI robotics work, really to scale all of this up, we have to do this in a commercial setting where we can deploy robots at large scale, automated tasks that people actually care about, and have this all running in a self-sustainable manner, where the systems that we're already deploying is generating real value. And through all those experiences, we improve the learning system. I think that was the key realization for me to decide to start Covariant.
Now, at the time, you're actually working on meta learning, right? Learning to learn, both for reinforcement learning and imitation learning. It's kind of interesting that in what you said earlier, kind of coming full circle in that you want our covariant robots to instantly learn about this long tail scenario on the fly, because when it's part of a sale, it'll be there for the next few hours continually. You need to adapt right away. But maybe take us back first. You wrote some of the earliest modern era papers on learning to learn for reinforcement learning, for imitation learning. How do you decide to work in that direction, which was not a common direction? There was not a lot of work happening there. How do you even decide that was interesting? And from there, maybe, how do you see that field has evolved from where it was back then to how do you look at it today?
Yeah, it's a really good question. I remember that I didn't start out like say, hey, this is the direction I want to go in. I think the story was like, I was really amazed by some of the advances in deep reinforcement learning at a time when I started my PhD. I think it was when we were first seeing robots learning from just its own experience, like learning to walk, learning to play video games. But the catch is that it requires a vast amount of data for it to acquire such behaviors. And there's not a lot of like transfer from earlier tasks. And how they for is kind of stupid to humans, to be honest. It's kind of just like doing very naive random exploration. And if you actually see the robot in action in real world, luckily we did a lot of experiments in simulation, but in real world, it will be quite painful to watch. You have like say robot dogs or robot humanoids just wiggling everywhere and hoping to learn like how to stand, how to walk, and so forth. And if we compare that with the human learning process, we can explore the world in much more in a much more sophisticated manner, where we have like low level skills that we reuse. We reason about how we explore different options, and we can learn rapidly based on our interaction. I think one example, Peter, you gave back then was like you're like moving to a new house and like you're trying to find where the shower head was. And there's probably like some typical location where people assume where that is. And then if it's not there, then like maybe you'll look somewhere else. But you do so like in very rapid manner, and leveraging a lot of provider, maybe within a fraction of a second. And those type of like, I guess, skill, learning and reuse, and like high level, like reasoning about, what you can leverage from your past experience. Those are things that are kind of lacking in the reinforcement learning algorithms that we've had. So there's a field for, or like a subject under reinforcement learning called hierarchical reinforcement learning. That's kind of focused on like giving the, learning algorithm or the agent more structure, like, maybe explicitly think about what skills it should first learn, which then, it can leverage to learn, more long horizon or more challenging tasks. So at the time I was, banging my head against this problem. I really wanted to solve it. But I didn't go very far. And I think the realization I came to is that maybe those things shouldn't be placed into the algorithm or the structure of the agents. Maybe those things, should themselves be learned from data, like, what skills should exist? What should be the learning algorithm's behavior? And at the time, meta learning has already, started having some signs of life in other domains, not in robotics, like in computer vision, many computer vision at the time. And the philosophy of that is, rather than using data to improve the system's performance under a specific task, you try to use data to improve the learning process itself. And the kind of analogy for computer vision would be like, rather than needing like, collecting, labeled, say, pairs of image classes, and then use like, say, some optimization algorithms to learn the parameters of neural networks. You will actually come up with some structure that's, taking maybe even a few examples, that we give to the system and give it the capacity of computation to learn whatever it needs, based on those examples, so that it can, make, more correct predictions when presented with new examples. And the analogy for, robotics for reinforcement learning is that, maybe we can, take inspiration from this and actually, use the previous, data or any sort of data we can think of to influence how the agent explores, the world, or to learn from its past experience. And I guess the analogy for humans is that, when we learn like new related skills, the incremental effort, becomes lower and lower. Like if we, learn to play the piano, as you become more proficient, the effort of like learning a new piece, and the similar difficulty becomes like easier and easier. And so I think that was kind of like, all of the considerations that kind of I was going through when thinking about like starting to explore meta learning. And that basically, if we want the machine learning algorithms to be more successful, and to have truly intelligent AI, they must be able to leverage what they've learned in the past to help them learn better in the future. So I guess that, yeah, if we think about like where meta learning is today, has been a few years, I guess, since I was doing pure academic research. But I think it's actually been really exciting. And I think one of the most exciting development maybe it's actually through other related fields. And I was speaking more in particular the large language models. And there's actually some very converging themes, because in those models, you can prompt the models to then perform a very diverse set of downstream tasks. And those prompts can maybe include like a few examples that you're giving to those models. And the tasks that they can then perform will include such as like writing poems, answering like customer support questions, querying database, and so forth. And I guess if we view this capabilities through the lens of meta learning, I think the process that was used to train those large language models, which is basically extremely simple. We're really just trying to get a model to predict the next possible word. It's such a simple algorithm, and through that, and through the vast amount of data it has seen, it has acquired this behavior to quickly learn and adjust what it should do based on like the past token it has seen. I think it's been really exciting, and I'm very excited about such advances starting to get applied and actually getting deployed to things other than the language domain. And for example, like getting new visual semantics understanding or new robotic manipulation skills from its own trial and error. So it's definitely still active area of research. I think we are actually going to start seeing this happening at Covariant in our systems.
Very exciting, Rocky. Now, switching from the technical to maybe more your personal path in some sense, you are likely the single most productive person in the world, as far as I can tell. And as far as many people tell me who work with you. Any productivity tricks you can share?
Yeah, thanks, Peter. Because I can't really say that, or I guess I know so many talented and very productive people, I guess, around my life, and of course when I Covariant is. So I feel very lucky to work with so many great people here. But since you asked, I guess like I have to share something. I think maybe one tip, and I guess this is also maybe more from me observing other people, since I'm bad at observing myself, is that it pays off to invest some effort consciously to make you more productive. Some examples could include like learning to use productivity tools, like trying out like a new development environment. I guess this is more specific to computer science, I guess, like new IDEs, new shortcuts for like GitHub Copilot, which I recently found to be a great productivity helper. Highly recommend people to try it out. I'm not taking commissions, just to clarify. And or in more specialized domains, build tools to make myself more effective. And I guess that could be I think the power of software makes like automation kind of like a central philosophy of what we're doing on day-to-day basis. And of course, learn from others. If you find some other people is highly productive, then try to see what you can learn from them. And one more thing I will say is that, and I feel like I realized this more and more from my time at Covariant, which is that rather than just focusing on the day-to-day productivity, it could be more important to keep an eye on the high-level direction, whether like you're working on the most important things towards whatever goals that you're setting out for yourself. And sometimes it's even helpful to maybe take some time to zoom out and revisit what you're doing. The worst case you want to avoid is like you are being productive day by day. You're matching like maybe like an instantaneous velocity. But if there's actually more important or more impactful things that you could be working on rather than what you're doing at the moment, those could be much more important productivity improvements than just focusing on the moment.
These are some great advice, Rocky. Thank you for sharing. And one of the things you said reminded me of the beginning of your PhD, actually many years ago. You said sometimes you want to explore tools. You might want to build some tools that make you more productive. I remember that you built a little tool that allowed to easily launch experiments on AWS that made you a lot more productive. But of course, you shared it with the entire lab, with other people and so forth, and made everybody more productive around you because they could launch their experiments so much more easily at scale than they could before you had built that tool. And being able to, I guess, build those tools that don't exist yet that make you more productive is quite a superpower too. Now, I know you work really, really hard, but I got to imagine that sometimes you try to relax and get away from things. What are some things you like to do to truly relax?
And I do think it's quite important to have a balance and to take time from work and to kind of recharge yourself. The few things I enjoy. One is hiking. Right now I'm kind of traveling back and forth between Hong Kong and Bay Area. And luckily, like in both areas, there's a lot of like good trails. And I enjoy hiking with friends and so forth. And in Hong Kong, I'm actually raising a rabbit together with my wife Zhao Yu. Its name is Puffin. I'm very adorable. I guess great temporary distraction from work when I was there. Of like now just playing with it. And actually recently I've started to learn to play piano. Again, kind of inspired by my wife Zhao Yu. She rented a piano about a year ago when we moved into the current apartment in Hong Kong. And so I think my initial motivation was to kind of increase its utilization rate. Maybe I should give it a try. And it turns out to be very rewarding. It's definitely kind of hard to learn, which is also interesting, I guess, to someone who's thinking about learning algorithms. And I quite enjoy it as a kind of context switching for work.
This really, thanks for sharing, Rocky. And this reminds me actually of something I maybe should have made part of your intro, but I'll share it now here at the end, is that at Berkeley, when you were an undergrad student, you founded the Chinese a cappella group. And so music is kind of part of your life for a long time. And it sounds like you switched from singing to piano playing now.
Yeah, I guess I wouldn't really call it switching, though maybe like, I see piano as maybe slightly less disturbing to neighbors. Although maybe our neighbors might not completely agree. And yeah, I guess both are quite enjoyable.
So you're still singing today?
From time to time, yeah.
Well, anybody listening, if you search for the Berkeley Chinese a cappella group, somewhere out there on the internet, you'll find some beautiful recordings. I've actually heard Rocky sing, and it's really impressive. So yeah, go find it when you have a chance. Well, thank you, Rocky, for making the time. Such a great conversation.
Thank you, Peter. Well, I really enjoyed this.